Hey there, algebra students. This is the chapter 10 practice test, and did this during a Zoom, but it was just choppy and decided it'd be best to do it again. Okay, let's describe the domain and the range of the function. Should have describe highlighted as well. To find the domain of a square root function, which this is a square root function, as you can tell by having the square root, you take the radicand, which is x minus 4, so whatever inside of the radical, and you write that as having to be greater than or equal to 0, because of course you can't take the square root of a negative number. So solving using the addition property of inequality, you get x is greater than or equal to 4. Okay, the range. So what a square root function's graph looks like, I'll draw a little sketch of it up here, is kind of a half parabola on its side. The parent graph would have a kind of a it's not one, but it's like a vertex here at 0, 0. This part is dashed, and that would be the other part of this like a parabola on its side, but we don't take the negative square root of a number. We only take the positive square root of a number. So when we take the square root of x, we get a positive value, not a negative one. And this is in part because we don't want to get two outputs for the same input, because this wouldn't be a function. So we only take the positive square root. So now, if you remember correctly, we have transformations, which are a, h, and k. So in this case, we have a horizontal translation 4 units to the right. Remember, if the minus or plus is inside the function, it's a horizontal translation. When it's minus, it actually means translate to the right. So this function was translated to the right. That's like a vertex. And therefore, we have a range of y is greater than or equal to 4. Or 0, my bad. Okay? All right, so let's look at the next one. And let's see if, well, I guess I can do, yeah, okay. And see if we can do this. Now, let's try this graphically first and see if that helps. I like how Caitlin Vogel during the Zoom today, she said, yeah, I think of it graphically. So this is a square root function. It has like a vertex. It's not a vertex. It would have been at 0, 0, but we have plus 3 that's inside the function. It's a horizontal translation 3 units to the left. And then we have minus 2 outside the function, which is a vertical translation 2 units down. So this would be a half a parabola going up like this, right? But there's also this negative in front, which is a reflection in the x-axis. So instead of going up from left to right, it's going to go down from left to right, like this. And just with this graph alone, you can actually figure out this domain and this range. But let's say we are going to do it using algebra. We're going to figure it out algebraically. So that radicand, once again, like the last problem, has to be greater than or equal to 0. And when we subtract 3 from both sides, we get x is greater than or equal to negative 3, which is exactly what we have here, right? So x is greater than or equal to negative 3. And then this, where do we have y values? Well, we have them when y is less than or equal to negative 2. So making a little sketch of the graph can really help with figuring out those ranges. All right, so let's move on to the next problem, which is a graph. Okay. So it's really important that whenever you are graphing a function, first you identify what that function is. This is a cube root function. A cube root function, I don't know if you remember this, but hopefully you do. It is an S shape where it kind of goes through 0, 0 and then goes like this. And really what this is it would have been like a sideways parabola, but this bottom part kind of got reflected in the y-axis and is going the other way. So once again, this has like a vertex, and the parent graph of a cube root function has kind of like a vertex at 0, 0. So just like the other ones, you're going to have an HK, which is going to be kind of where that vertex ends up based off of the horizontal translation and the vertical translation. So I have my x and I have my p of x, input and output, and because it has a like a vertex right here, And because it goes in both directions, this is kind of like the middle of the graph. This vertex thing is like at the middle of the graph. It's not a vertex, but it's like one. And its location is at hk, so it's actually at +3, +2. Okay? +3, +2, because it's 3 units to the right and 2 units up. But now the thing is, if you substitute 3 in for x, you'll notice 3 minus 3 is 0. That's a perfect cube. 0 is a perfect cube. The cube root of 0 is 0, plus 2 is 2. So in other words, what we want is we want whatever is inside the radicand to produce a perfect cube so we can take a cube root. Well, perfect cubes come in from the negatives, right? Because they go on to the negatives. You can take the cube root of a negative number. So what I like to do is I like to use these perfect cubes: -8, -1, 0, 1, and 8. And then, of course, they go on forever. But those 5 points, whenever you're graphing a perfect cube or a cube root function, those are the numbers that we're looking for to end up in the radicand. But that's not the same as x, because we already did 0. We substituted 3 in for x. 3 minus 3 is 0. But say I wanted to do 1. What would x have to be so that x minus 3 equals 1? Now I could write that as an equation. X minus 3 equals 1. Add 3 to both sides, and you get x equals 4. And the important part of that is that 4 minus 3 is 1. So the cube root of 1 is 1. You add 2, you get 3. Okay, now the next one is 8. The next perfect cube is 8. Well, what would x have to be so x minus 3 is 8? It'd have to be 11. So 11 minus 3 is 8. The cube root of 8 is 2, plus 2 is 4. But now we can also get -1 inside the radicand, because that's a perfect cube. So what minus 3 is -1? That's 2. 2 minus 3 is -1. The cube root of -1 is -1, plus 2 is 1. And then we can get -8 in the radicand. That would be -5 minus 3 is -8. Cube root of -8 is -2, plus 2 is 0. So what we want is -5, and then we get is it 0? I already forgot what it was. -2 plus 2 is, yeah, 0. Okay, let's graph these points. We have 3, 2, which is like the vertex. It's not a vertex, but it's like one. We have 4, 3, and we have 2, 1. Now, I would say these 3 points in the middle, notice the danger here. They look like a line, but they aren't. They aren't a line. They look like a line, but they aren't a line. -5, 0 will prove that. -5, 0 is somewhere over here. So that's clearly not a line, because that point would never be on the line. So what we have is we have the left side of this S shape. I didn't draw it very well, as you know, but the point is clear, right? That this is part of this S shape, which would go on this way, right? Just like this. All right. Next, number 4, this is a square root function. So the square root function is a totally different looking graph, right? It's just going up like that, trending upwards. It doesn't have the left side because we can't take the square root of negative x values. For instance, in this one, I would still find the like a vertex. It's pretty important because it shows you where you're starting from. So whoops, I should have said x and n of x. If you think about this as the like a vertex is at 0, 0, this translation is down 5. So that like a vertex is 0, -5. Now, the nice thing is there's nothing else here underneath the square root, so we could just pick perfect squares. The perfect squares are going to be, that we're going to use, are 0, 1, 4, and usually I go up to 9. But you know, you could use any of the perfect squares. It's just you want to be mindful of where that kind of like a vertex is, that smallest value you can take the square root of. And I just realized this is not like a cube root function, so I don't know why I wrote 0, 5 way over here. So I'm going to write it actually closer to here. Okay. Just to make sure you remember this, if I was looking for the domain of this function, I would take anything under the radicand, which is just x in this case, and it has to be greater than or equal to 0. Well, that's clear because we're just taking the square root of x. There's nothing else to, no operation to do. So I could just go to 1 next. right? Square root of 1 is 1, minus 5 is negative 4. I can go to 4 next. Square root of 4 is 2, minus 5 is negative 3. And so I get 0, negative 5, 1, negative 4, and 4, negative 3. And you can see that you get this square root shape, half a parabola kind of on its side thing, and we're done. Pretty easy. Okay, this one also easy because there's nothing to worry about inside the radicand. So this is just, we can just pick perfect cubes. And like I said, here are the perfect cubes that we usually use. 0 is the one that's going to be in the middle. So the cube root of 0 is 0, plus 1 is 1. Cube root of negative 1 is negative 1, plus 1 is 0, so negative 1, 0. Negative 8, cube root of negative 8 is negative 2, plus 1 is negative 1. So we're going to have negative 8, negative 1. And then we're going to have, let's see, 1. Cube root of 1 is 1, plus 1 is 2. And finally, 8. Cube root of 8 is 2, plus 3 is, sorry, I said that, didn't I? Cube root of 8 is 2, plus 1 is 3. Okay, yeah, there we go. 0, 1. 1, 2, negative 1, 0, and then negative 8, 1. That's way over here. So we know that this, as we make the graph, it's a cube root function, we should not get down to negative 1. It's going to go in that direction. It's not going to get down here to negative 1 because that won't happen until x is negative 8. And then it goes up, and then let's see, well, 8, 3. That's way over here, so it's not going to get up to 3. And so we do something like that. And we get our graph. Awesome. Okay, next one. This one's a little harder. It's a square root function, so we're expecting to have this kind of shape. But we should restrict that domain right from the beginning. Where is our domain? And I guess I'll be consistent and do it down here. The radicand has to be greater than or equal to 0, and therefore x must be greater than or equal to negative 2. Okay? So that means that negative 2 is our first input into this function. So what I'm going to do is have x and f of x, and the first value that I substitute in is this 1 on the right side of my domain, my inequality statement that expresses the domain. Okay, so negative 2, if I substitute that in, negative 2 plus 2 is 0, and then there is no negative 0, so it's just negative 2, 0. Next, just like here, I have my perfect squares. I need to select an input so that plus 2 I get 1. So x would be negative 1. Negative 1 plus 2 is 1. The square root of 1 is 1. Negative 1 because the negative on the outside. Then 4. What can x be? So x plus 2 is 4. It's 2. 2 plus 2 is 4. Square root of 4 is 2. And then it's going to be negative. And that's actually enough points to graph this. So negative 2, 0, negative 1, negative 1, and then 2, negative 2. And you can see we get this kind of half parabola shape. Whoa. Sorry. And it goes down that way forever. Couple important things here. This should be the bottom half of the parabola, like a sideways parabola, because of this negative out in front, which is going to reflect it in the x-axis. Okay, let's end that with part 1, and then I can come right back for part 2.